Okay, so today we are going to be learning about how to solve some PDEs, and we are going to be focusing in 2 dimensions. And I'm going to start off with a general method. Okay, so this is going to be the subject of the lecture today. So we are given, suppose we're given a second order linear partial differential equation in 2 dimensions, x and y, with the dependent variable being psi, such that we write this general equation as a of xy psi xx. So two of these things downstairs means it's just del 2 psi del x2 plus twice b of xy. This is going to be what xy plus c of psi yy. Again, c is also a function of x and y, psi yy. This is equal to sum d, which is a function of psi, I mean the first derivatives, psi, which is implicitly also a function of x and y. Okay. Now suppose we are given Cauchy boundary conditions on a smooth curve C. Okay. So Cauchy boundary conditions on a smooth curve C. So that's on C, we have the following. We have what? We have psi of xy is on C. This is something that's a form that you have. Let's call the small a. And you also have del psi xy on the curve. So this is the so this is going to be del psi del n, which is equal to b of xy. Now, what we would want to do is we would want to discuss if it is at all possible to determine psi in the vicinity of some point x naught y naught, which is on C. Okay. Now, with this in mind, what we will do is we will summarize what information is contained in these Cauchy boundary conditions above. Okay. So now let's let t cap be the unit tangent at a point on C. So given xy on C, we will know this given psi of xy, we know the tangential derivatives, right? So what is that? That's just the unit vector modded with the left side. The tangential and normal derivatives would constitute two linearly independent derivatives in two dimensions. So thus what we can do is from these we can deduce both psi, del psi del x and del psi del y on C at each point. Okay. Now, if we also assume that the boundary conditions ax and axy and bxy are infinitely differentiable along the curve, then we know these all order tangential uh, tangential tangential derivatives psi x and psi y. And these again, what they'll do is these will again constitute certain linear combinations of successive higher order uh, partial derivatives starting with this second order. So now the problem is boils down to finding if and under uh, what conditions one can obtain the solution in the vicinity of this curve C. So what we will be discussing here is a method that is going to be valid for a solution which is analytic in these two variables x and y. And by being analytic in x and y, what we will do is we will refer to the existence of a Taylor expansion uh, of the function which is convergent in some neighborhood of in these two dimensions. So let's be precise about that. So uh, analytic function in xy. So a function of n real variables psi of x1 to xn is analytic at a point. Let's just denote this point with naught. So x naught 1, x naught 2, dot dot x naught n. If it can be Taylor expanded so that would essentially mean that psi of xi is psi of x naught I plus summation over j equal to 1 to n del psi del xj. Here xi is equal to xi naught into xj minus xj naught plus dot dot dot, and the nth term is going to be the following. Let's just write it down. So this is, you just need to n1 n2 dot dot n n is equal to sum over all ni factorial n by factorial n1 factorial n2 dot dot factorial n del n psi by del n1 x1 del n2 x2 del nn xn at, of course, so let me, since I'm running out of space, let me just pull this inside a little bit. Okay, and so this is, of course, at xi equals xi naught. This is going to be multiplied, of course, by, you have xi minus xi naught, x1 minus x1 naught to the power n1 dot 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 xn minus xn naught. Sorry, not there, whole to the n. So this is the nth term, and this is a representative term, and so on. So this is going to be the way that these things are expanded. So this is going to converge. So this, which converges in some neighborhood of xi naught. Okay, so that's what we mean. So in our case, this is going to simply be the thing for the two variable in our case. This is simply psi of xy being equal to psi of x naught y naught plus psi x into x minus x naught plus psi y minus y naught plus half psi xx x minus x naught squared plus psi xy y minus y naught x minus x naught y minus y naught plus half psi y minus y naught squared plus so on and so forth. So you can essentially write this down in terms of a series where n1 and n2 go from 0 to infinity, and you have dn1 plus n2 of psi del n1x del n2y at x naught y naught into n1 plus n2 factorial by n1 factorial n2 factorial x minus x naught whole to the n1. And again, I'm running out of space, so I need to move this. Y minus y naught whole to the n2. Okay, so now we can determine an analytic solution in the vicinity of the point x naught y naught on this curve C if the coefficients of this expansion, which are various order um, derivatives of psi, this can be determined at this point x naught y naught. So this is what we would try to determine systematically as we go along. Okay. Now we had this smooth curve. So we will parameterize the smooth curve by S. Okay. And this S is the distance which is measured from some fixed point. So parameterize C, such as So what is going to happen? So x is going to be labeled as x of s, and y will be labeled as y of s. Okay, and these are you know s takes values between a and b. So then what is going to happen is the unit tangent and the unit normal to the point at an arbitrary point s naught are going to be given as the following, right? T cap is going to be the unit tangent, that is dr by ds by modulus of dr by ds. So this is what, this is just x prime s I cap plus y prime s j cap, and for example n is going to be just y prime, so that is s I cap minus x primed s j cap. You can read off what n is from t just by demanding that n dot t is equal to 0. The knowledge of psi of s in the vicinity of x naught y naught is now parameterized by s equal to s naught, and this allows us to evaluate psi prime. So psi prime at s naught is, as we have seen, t dot grad psi. So this is simply x primed s naught psi of x plus y primed s naught psi y. And the knowledge of del psi del n at x naught y naught allows us to evaluate the another independent uh, linear combination of the first order derivatives. So what's going to happen is del psi del n in that case is going to be given by y primed s psi of x minus x primed. So these are all knots, okay? S naught psi of y. So what do we do? What do we have? So we have now found both the first order derivatives, psi of x and psi of y at s equal to s naught. And this essentially applies to every point on C, which is parameterized by S. Okay. So these determine first order derivatives. And now we want to move on to second order derivatives. Okay. So now we will know that we have, okay, now for second order. Now second order. So we want psi xx, psi xy, and psi yy. Okay. Now notice that we are going to have these this number of sources of information for this. So let's just jot them down. So the three sources of information. Number one is the PDE itself, where you can substitute uh, where uh, psi psi x psi y at s equal to s equal to s naught are substituted. So that's one source of information. Second source of information is a knowledge of del del s of psi of x s. This you can already, I mean, this can be this is from psi x, okay. And similarly, the third is the knowledge of del s of psi of y. It is, this one will be from psi of y. This has already been I mean, determined for this range. So now, given all of this, let's see how we can extract the second order uh, second second order derivatives, if you wish, of the function psi. Okay. So the first one is essentially a of xy psi of xx plus b twice bxy psi of xy plus c of xy psi yy. This is equal to d of psi x psi y psi xy. This is known quantity. Similarly, x primed of s naught psi of xx plus y primed of s naught psi of xy is equal to del s of psi of x at s naught. This is also known. And also x prime s naught psi of xy plus y prime s naught psi of yy is equal to del s psi of y s naught. This is also known. So you can bring all of this together and write it in the form of a matrix, which is like A to B, C, X prime S naught, Y primed S naught, 0, 0, x primed s naught, y primed s naught, and this is psi xx, psi xy, psi yy, and this is a known vector. Okay. So this equation can be solved for all of these. So this thing can be solved. So this can be solved for all derivatives, all three derivatives at s equal to s naught, if the determinant of this guy determinant is non-zero. Okay. All right. So yeah. Okay. All right. So what we were saying is that this can be solved if the determinant here is non-zero. So in order to proceed, what we will assume is that the determinant here is non-zero. And this is satisfied at each point in some neighborhood of the point s equal to s naught on the curve. And hence what we will do is what we have seen is that all the second order uh, derivatives will be determined at every point in this particular neighborhood. Okay. So let's just say here, assume this holds. In some neighborhood of s equal to s naught, and hence all second derivatives are determined. Now remember that we have to not only do first derivatives and second derivatives, but we need to understand all of these guys. Okay. So now let's look at third order things. So now we have these four of these. So we have psi xxx, we have psi xxy, we have psi xyy, and we have psi yyy. Okay. Again, there are the following sources of information. So the information is, number one is two first order derivatives of psi of the PDE, where you're going to put in the values of psi x, and psi xx, psi xy, etc. at x equal to x2. And second is knowledge of psi xx, psi xy, psi yy along the curve. Okay. So let's now first think about what we can do with the PDE. Okay, and let's differentiate it with respect to say x, and in that case, the equation that you're going to find is axy Yeah, so just remember that a, b, and c are all functions of x and y. So a psi xxx plus twice b psi xxy plus c psi xyy. So this is known, right? So this equation involves three out of the other, out of the four things that we are interested in. We seek, we want say additional relationship involving these three. Okay. Uh, so what we do is we remember that it's possible. This is something that we can do if we differentiate the known quantities psi xx and psi xy along the curve at s equal to s naught. And so then what we have is we have x primed s naught psi xxx plus y prime s naught psi xx y. This is equal to del del s of psi xx, that is equal to s naught, of course. This is of course known. And remember, similarly, what we can do is we can differentiate this one as well. S naught of psi xxy plus y prime of s naught psi xyy. This is del del s of psi xy at s equal to s naught. This is also known. Now with these three these guys, I mean taken together, uh, you can solve this provided again you have this delta, which is again a twice b c x prime s naught y prime s naught 0 0 x prime s naught y prime s naught. This is not equal to 0. So this is, as you have just seen earlier, this is precisely the thing that we had earlier. So assuming this is fulfilled at s equal to s naught like we did before, so we can solve these equations. And what we now do is, since we know all of these guys, so what you can do is you can substitute the thing in the additional equations to just recover what psi y is, right? So um, so that is something that one can easily do. And so what you can actually uh, you know verify to all orders is that if you were to just maintain the thing that we showed here, then you can actually show that all the derivatives of psi xy at any can be obtained at any point where this determinant is actually non-zero. Okay. So that's so we have been able to, in that case, show you that we would be able to um, find a solution to this second order equation by just looking at. So these are the ways that you would be able to solve it. um, So remember what we did. We started off with a second order equation, and we had these. So this was this general second order equation, and we had, Cauchy boundary conditions on a smooth curve. And then we were trying to discuss if it was possible to determine psi at any given in the given in the vicinity of some given point x naught y naught, and we showed you that this is something that can be done, and so so you we what we found is that, if we restrict ourselves to something, a function which is like this, we would be able to uh, we would be able to find out all of these guys, which are the coefficients here, and we can do this systematically. And so this is what we have done. All right, so this is something that we have shown in 2 dimensions, and going forward we'll use these things as well. But before going on to do anything more, let's just show you quickly, let's show you an example. Okay, so let's look at an example, and in this example, let's look at the wave equation. And we have with it Cauchy boundary conditions. Psi of x0 is equal to 0, del psi del t x0 is equal to 0, minus 1. So we want to verify that one can evaluate all partial derivatives of psi of x at, for example, the point 0, 0. Okay, so let's try and do this. So del psi psi n del xn at x0 is equal to 0. This is something that you can obtain n equal to 1, 2, dot, dot, dot. This is from the value of psi in the interval in minus 1, 1. Okay. So if this is, since psi is equal to 0, psi of xy is equal to 0, then psi of xy del n of this is also going to be equal to 0. And from the value of del psi del t, from del psi del t in the neighborhood of minus 1, 1, what we can obtain is del n plus 1 psi del n x del t. This is equal to 0 for, again, this range. Now if you do this, if you find these two, and remember that from the wave equation itself, the wave equation is psi xx is equal to psi tt, and we want to find all of these guys, right? So now what we can do is, so psi tt of at x0 is equal to psi xx at x0. We have found psi xx at x0. This was 0, so this is also equal to 0. So psi ttx at x0 is psi xxx at x0. This is equal to 0. Similarly, you can go on doing this. Psi tt xx at x0 is psi xx xx at x0. This is equal to 0. And we can also employ we can, so this is, you can start from psi xx, or rather, uh, psi tt is equal to psi xx again, and you can take a time derivative now. So you will get psi ttx is equal to psi txx. Now, from the fact that you already have looked at something like this here, so this is psi t. So you know psi t of xx is equal to 0. So this guy again will have to be equal to 0, right? So you can, I mean, continue in this line, and we can prove that all partial derivatives of psi of x. So all partial derivatives of psi of xt on the curve t equal to 0 minus 1 less than x less than 1 can be determined and R0. Right, so this is what I wanted to say for this lecture. And yeah, so I've shown you a way that in which you can look at general methods in 2 dimensions. We shall be moving on to other interesting things in the next lecture. So until the next lecture, then, um, we yeah, so that is it for now, and I shall be seeing you again in the next lecture. All right, bye bye.